Hi, I'm Adam Smith. I'm an associate scientist at the Missouri Botanical Garden, and this is a short introduction to retroactive georeferencing of herbarium and museum specimens. So what is georeferencing? Well, in this context, it's going to be interpreting a verbal description of a locality, for example, 10 miles north of St. Louis, and then converting that into a longitude and latitude pair, plus a numerical description of the uncertainty associated with that verbal description, plus any kind of errors that we as a georeferencer might introduce. This here on the right is an outline of this introduction. First, we're going to motivate ourselves with a challenge and describe how difficult it can be sometimes to interpret what seems like a simple statement of location and translate that into numerical values. And then very briefly, I'm going to mention what Tropicos, which is the Missouri Botanical Gardens database, does in terms of georeferencing. And then for the most part of the talk, we're going to focus on this point radius method, which is a standardized set of rules for interpreting different types of locality descriptions and then assigning them coordinates and uncertainty. And they're different, here are the different types of descriptions. And then finally, we'll end with some tips and tricks and some flowers. So let's motivate this. In 1932, I went 10 miles north of St. Louis and I buried some gold bars. And if you want those gold bars, you can go and dig them up and you can have them. Well, if you're still listening and you haven't left to go dig up those gold bars, let's spend a moment and deconstruct the uncertainty inherent in that statement, 10 miles north of St. Louis. And this is somewhat of a ridiculous example, of course, but you'll see that it really forms the crux of just about everything else we're going to be doing. So let's start with that first term, 10 miles north of St. Louis. Now, 10 is a nice round number. 1932, when I buried these gold bars, was I just kind of guesstimating, or did I really mean 10.0000, et cetera, miles, like exactly 10 miles or not? We don't know. So what's the next term? North, miles, 10 miles north of St. Louis. Well, let's assume perhaps I was accurate to within half a mile. So maybe I meant 10.5 miles or 9.5 miles. So 10 plus or minus 0.5 miles. 0.5 miles is a greater uncertainty than if I had measured my units in kilometers. If I had said equivalent would be about, I don't know, but 12 kilometers north of St. Louis, plus or minus half a kilometer, that plus or minus half a kilometer is smaller than plus or minus half a mile. So the units are also important in this case in terms of it defining our uncertainty. Next term, 10 miles north of St. Louis. Now, when I meant north, did I really mean northeast or northwest? Was I kind of eyeballing it? Or did I mean due north, something like that? And then the last term of St. Louis, well, in 1932, what was St. Louis? It was different than it is right now. So in general, it kind of looked like this on a map, but the north side of St. Louis, I honestly don't know where it was, but it was probably in a different location. And for that matter, was I actually thinking about 10 miles north of the city limit of St. Louis, or was I thinking about 10 miles north of more or less like downtown or something like that? If you're from this area, you'll also know that there's St. Louis City, and then there's the larger kind of conglomerate of urban areas. And depending on who you're talking to, sometimes you'll call the larger conglomerate St. Louis. So maybe I was thinking of not just the city, but the larger area. And confusingly, there's St. Louis City and there's St. Louis County. They're administratively distinct. So when I said St. Louis, was I really thinking of St. Louis, the entire kind of kibosh? So you can see in this very simple statement, there's a lot of uncertainty inherent in how we'd interpret this and how we would geolocate these gold bars. So to bring this back to herbarium and museum specimens, here's what we're talking about. This is a sample taken by George Yuskevich in 1989. It's from Missouri. And here's the locality description. So Scott County, Missouri, 0.6 miles south of milepost 79 marker on Interstate 55. Now, we could physically drive out there, find mile marker 79, and then walk about 0.6 miles south of there. And there's other parts of the description here. But this is fairly exact, but even so, there is some uncertainty in that. So 0.6 miles, does that mean 0.6000 miles? Or is it 0.6 plus or minus 0.05 or something like that? So you can see how there's uncertainty inherent in this statement. And I'll also point out there are different ways to geolocate things, sometimes on the same specimen tag. For example, this part right here, T28 and R14 East, etc. That's the Township range section quarter method of geolocation, which is kind of like a pre-GPS GPS sort of system. And that's found in the US. But anyway, there are different ways to describe where a collection was located. And we're going to dive into how you might interpret each of these segments to really geolocate this particular specimen plus any others. Before we go any further, though, I want to talk about, I have to mention really what the Tropicos does. And Tropicos is the botanical garden, the main database of the Missouri Botanical Garden. So in Tropicos, we have two different kinds of records that are georeferenced, and you can see them here and here. Each row here represents a different plant. So these records do not have the square brackets around them. You can see that. And in this case, they're only geolocated to the nearest minute. So we have degrees, 39 degrees, 52 minutes. You could get into seconds. These don't have that. But whatever the case, they do not have square brackets around them. And so these are interpreted as accurate records to whatever level. I can't say, but they're interpreted as accurate records. In contrast to these records, you can see they have the square brackets around them. These are geolocated more or less to the center of the smallest geopolitical unit to which they can be located. So in this case, for example, this record is geolocated to the center of Lonoke County in Arkansas in the United States. And sometimes you wouldn't even have a county listed, maybe just have a state, in which case these coordinates refer to the state center more or less. So for the rest of our presentation, I want to focus on the point radius method. And this was introduced in 2004, and it's undergone a little bit of revision and refinement, but basically the same process is the same as described in this particular paper. So the point radius method has a very particular philosophy that can be kind of embodied by this statement by the philosopher Carveth Reed, which if you're going to be a philosopher, that's a great name to have. And this is paraphrasing. It's better to be roughly right than precisely wrong. If we were to translate that into georeferencing, what we're saying is that it's better to be uncertain about a specimen's location than to assert that it was collected in a specific place if we're not confident in that assertion. So in other words, we might try to get into the mind of the person who was collecting something and say, you know, I'm pretty darn sure it was at the junction of these two, say, roads or something like that. But unless the person says something very specifically about that, all we can geolocate that reference to is perhaps a larger area. And so we should indicate that and use the larger area. Now that might be a little bit of miss because the larger area might include some places that are really not relevant, but it's better to do that than to assert it was collected in a much smaller location and possibly be fairly wrong in that. As a corollary to this, if we're unsure about how to georeference a record, it's better not to georeference it at all than to take a wild stab in the dark. So let's go back to our motivating example, our gold bars 10 miles north of St. Louis. As we already described, there are many different locations that you might consider 10 miles north of St. Louis. So the point radius method would take a particular interpretation of this. So the point refers to the center of a circle, and I'm not showing you that center here, but you know where it is. And then the radius refers to the radius of a circle that encompasses the most likely location of collection. Now, the circle is not supposed to be under the point radius method. The circle is not supposed to be interpreted as a probability field in the sense that the center of it, the point, is the most likely area of location, and then the probability kind of degrades as you go out. It's not supposed to be interpreted that. Rather, it's supposed to be interpreted as indicative of every single location within the circle being an area of equally likely to have that collection. Now, in reality, that's probably not true for, in our example, there's the river here. Although now that I think about it, it probably would have been wiser to bury those gold bars in the river. But anyway, if you're collecting a plant, if it's not an aquatic plant, then the river seems a very unlikely place to have collected the plant. So that in reality, that's not entirely true, but that's the way it's intended to be interpreted. So just to be entirely clear, if you were to look at a series of records that you might have downloaded from, say, the Global Biodiversity Information Facility or GBIF or something like that, you'll get a ton of fields, but these are some of them. So you get a state, province, a county, municipality, which here is blank, but that would be like a city or something like that, and then a verbal description of the locality. So these all together are taken as locality, and then these can be translated into coordinates. And sometimes these are taken at the same time that a record is collected, but quite often they are also taken much later, and sometimes by interpreted by somebody much later, and sometimes by somebody who didn't even live at the time that the person collected it lived. So these would be our points of the circle, and then our uncertainty would be this value, which in GBIF is called coordinate uncertainty in meters. This is the Darwin core format specifically. So this refers to that radius. So before we go any further, though, I want to introduce you to a couple tools that will be very useful, and I'll show you how to use these. So the first of these is Google Earth Pro, and I'm emphasizing the Pro aspect because if you just Google Earth, it will take you to a web browser version of Google Earth, and it's very useful, it's very interesting, shows you the Earth, you can zoom in and zoom out and stuff like that. However, I have not been able to figure out how to upload into that version of Google Earth a KML file. And a KML file is kind of like Google's version of a shapefile. So rather, I'm pointing you toward a standalone program. It's free. You can download it. It'll install on a Mac or on a PC called Google Earth Pro, and we'll be using that. Another website, which you may have heard of, is called Google Maps. Now, why would you need Google Earth Pro and Google Maps? Ultimately, they should be drawing from the same database. Well, what I found is that Google Maps is usually better at parsing language or words than Google Earth Pro. For example, you might type something into Google Earth Pro and it'll simply say can't find it. You type the exact same thing into Maps and it'll at least suggest possibilities and often interpret it in hopefully a useful manner. So it's useful to use both of these. Another tool, which I'm sure you heard of, is Wikipedia. And but one thing you perhaps may not have noticed is that for pages that refer to places, so this is a place in Brazil, Barra de Garças in Brazil, on the right side at the top of the tab is this little link here called coordinates. I've zoomed in so you can see what it looks like. So this has the coordinates of what Wikipedia thinks is that place. And then if you click the coordinates, it'll take you to this page, a GeoHack page. And I'm not showing you everything there. There's a lot of information about the location, but in particular, it's these links here, which are very useful. And I'll show you how to use those. And the final tool, or really set of tools I want to refer you to are on this website, georeferencing.org, which kind of speaks for itself. A lot of resources there that we just do not have time to cover, but I highly suggest that, or strongly suggest that you check them out. In particular, though, I want to point out the Geo-Referencing Calculator. We'll be using this over and over here in the next few moments. The easiest way to find this is just to do a search for Geo-Referencing Calculator, and it should be the first link that shows. But otherwise, if you're on georeferencing.org, you click Tools, Calculators, and it'll take you to the Geo-Referencing Calculator. So here's what the Geo-Referencing Calculator looks like. I'll be explaining what the different boxes mean and things like that as we go through. So before we do that, though, I do want to point out some of the most important parts of the Geo-Referencing Calculator are actually the links down here. This is basically the manual, not just for this particular tool, but for how to georeference under a very robust, repeatable, scientific sort of manner. And it's a long document, but it's very approachable. So I highly suggest reading through that if you're going to engage in any kind of prolonged georeferencing exercise. These two links, as they might seem, refer to instructions on how to use the calculator. I'm happy to say that they've been updated for just recently, because for the last couple of years, you clicked on them and they brought up some old versions of the manuals, and some of these boxes weren't even explained. And then finally, this link here takes you to Google Sheets that shows you a list of tools and links And depending on what you want to do, it'll give you various options. For example, if I have the name of a place, perhaps I have the name of the place in an anglicized format versus a native format or something like that. Or maybe there are different ways to call that place. Then I can go here to the Getty Thesaurus of geographic names, type it in, and presumably it'll bring up a list of the most likely possibilities. And you can see here for the different tasks, they'll give you what they consider the best option and then sometimes an alternative to that if it doesn't work. So very briefly, here's the kind of layout of the land of the georeferencing calculator. The boxes on this side refer to uncertainty due to the person who collected the record, the specimen, and then described where it was. And then the boxes on this side, very generally, refer to your errors introduced when you are doing some georeferencing, since after all, we're not all perfect. So the georeferencing calculator is really structured around the idea that you can actually take these verbal descriptions of geolocalities and classify them. And there are different ways to classify them, and you'll find sometimes a particular specimen might have different kind of descriptions, but you can kind of break them up into these sort of categories. One might be coordinates. You just have some sort of coordinates. It might be GPS coordinates, or maybe somebody used a topo map or something like that. Another is location. So I might have just McPherson, Kansas. Another is a location plus an offset, 3 miles from McPherson, but it doesn't tell if it's north, south, east, or west, 3 miles. Location along a path. So in this case, 3 miles along Highway 61, southwest of McPherson. And then finally, oh yes, and location at a heading, so 3 miles southwest of McPherson, but that's more vague than distance along a specific path. And then finally, the public land survey system, which isn't in the georeferencing calculator specifically, but I'll show you how to use a nifty website to get it, in a sense, into the format that we would use in the georeferencing calculator. So if we switch over to the georeferencing calculator, I'll show you how it actually works. And here we are. So here it is. This is what it looks like when you pull it up. You click this box here and it gives you those different options for the different kinds of geolocality descriptions. So the first one we're going to do is coordinates only. We'll select that and all these boxes pop up. So let's go back to the example I want to show you. Let's georeference this particular specimen. And there are some verbal descriptions here. So 1 kilometer west of Portezuelo de Jamao. I tried to look this up. Honestly, I could not. So what we have rather is these set of coordinates. So it's, notice it says near, but it's near 31 degrees, 37 minutes north, 115 degrees, 39 minutes west. Now, this is important. You notice that the coordinates are only to the nearest minute. So we've got degrees and minutes. It doesn't go down to seconds. So we're only sure of our georeferencing locality to within the nearest minute. In other words, if it had been closer to 38 degrees north, we had assumed that they would put 38. If it had been closer to 36, we had assumed they would have put 36. So we're going to assume this is really 37 plus or minus half a minute. And I'll show you how that's reflected in the georeferencing calculator. But this is important because when we use degrees, minutes, seconds, say, versus a decimal representation, there's almost always inherent uncertainty in that unless you collect it exactly at that minute, exactly at that second. And that's usually hard to denote that you were collecting right at that particular location. So if you think about how longitude is arranged, you can think of it as lines that connect the North Pole with the South Pole. And at the equator, those lines get wide in the sense they get further and further apart, but at the poles they are very close, and ultimately at the exact pole they touch. You could put your foot down and literally on the pole and literally put your foot in all 24-hour time zones. So at the equators, those lines of longitude are very, very, very close to one another, within inches or even less when they touch. However, at the equator, they are the farthest that they are from one another. And at the equator, they are within about 111 kilometers from one another for 1 degree of longitude. And as you go north or south to 45 north or south, then they get closer, and the error or the difference between them, between 1 degree and the next degree, is about 78 or 79 kilometers. So if we had a record that was accurate to say just within 1 degree, we would have to add, depending on our latitude, if we're at the equator, plus or minus 1/2 of about this value, because we're not quite sure exactly where it was taken. Likewise, if we were to look at the error inherent in recording a location to the nearest minute, just like this record here, at the equator, and this is not at the equator, but if this is at the equator, then we would be only certain to within plus or minus 1/2 of this value, about 0.9 miles, something like that. So this is the kind of uncertainty, even when we have coordinates, that's inherent in this sort of description. So let's go back to the georeferencing calculator and see how we would use this to calculate not just the coordinates, which basically we already have, but the uncertainty inherent in that. So we've got 31 degrees north, 31 and 37 north, and let's put that in. So we've got coordinates only. Where are we getting the coordinates from? In this case, from locality description. If we were using a map or something, we might select that, but we don't. The coordinate format, so this is decimal degrees. We're not looking in decimal format. So we got degrees, decimal minutes. If we had seconds, we'd select that. Let's click this. And what was it? It was 31 degrees and 37, 31, 37 minutes north. And then longitude, we have 115 degrees, 39 minutes. And that's on the Western hemisphere. So make sure to pick that. So what is the datum? The datum is basically the model that we're using of the Earth. And if you're using a particular map, then you should know the datum because it would be printed hopefully on that. In this case, though, it's not recorded, so we're going to keep it as it is. Now, what is our precision here? Well, like we already discussed, we went down to the nearest minute. If this had been, say, 31:45, 115, 39, then all we'd be sure is that, or sorry, 115, 40 or something like that. All we'd be sure is that we're down to the nearest maybe 10 minutes or 5 minutes, depending on how these numbers might appear rounded. And maybe the person was trying to be pretty exact, but without any indication to that effect, again, going back to our philosophy, it's better to be uncertain than it is to be precisely wrong. Then you pick the more generous, so to speak, of these levels of precision. So in this case, though, we know it's down to the nearest minute. This box here is measurement error. I'll be talking about in a second. It's not so relevant in this particular case, so I'm just going to put 0. So I'm going to fill in 2 other boxes. Let's see, I'm going to say who did this. I did it. And the protocol we're using, basically it's this tool that you're looking at. So Geo-Referencing Quick Reference Guide 2020, and we're done. We click calculate. It fills in these boxes. So this is a decimal representation of these degrees minutes representation of longitude, latitude. Here's the uncertainty. That's the radius of our circle. We don't know the datum. This is the precision, how many digits these are good to, and then when it was georeferenced, which is basically right now. Who did it, of course, and then the protocol. I can click copy. And I forgot to open up my worksheet. So I'm going to do that here. The computer has to think about it. So why don't you grab some coffee or something like that? Oh, here it is. All right. And you know what? I didn't blank these out. Okay, pretend those weren't there. This is the record we just georeferenced as a Linanthus record, and I'm going to click Control V or paste on my computer, and it pastes it right in. And now we've got it all filled in. So we've got the species already filled it out. Latitude, longitude, the datum, the radius of our circle, our uncertainty, how precise these values are, etc. So you can see it's very handy. And when you click copy, you just paste it into your spreadsheet if you got it set it up like this. Okay, so good job. Give me a high five. We did the first one. So the next type of locality description is the named location. This one's a little bit difficult to see, but as you can see, it's Plants of Idaho and then Bear Lake. And just as an aside, I'll note it was collected in, I guess it would be August 9th of 98. Well, is this 1898, 1998? In this particular case, I know it's probably 1898 because the specimen was identified or re-identified in 1996, so it couldn't have been identified before it's collected. But just as a note, this kind of date format is really not helpful because time changes. So anyway, back to Bear Lake. We're going to look at the plants of Idaho and Bear Lake. And to find Bear Lake, I'll show you how we would do that if we were using the Wikipedia route. So we're going to go to Wikipedia, and that's going to take us to Google Earth Pro, and I'll show you how it works. So let's do Bear Lake, Idaho Wiki. That's my search. And it looks like Bear Lake is actually located in Idaho and Utah. We're going to assume that the person who took this record was really talking about Bear Lake, the Idaho portion, and not the Utah portion, but I'll show you how we reflect that. So remember this coordinates tab, we're going to click that. It's going to take us to our GeoHack page, and then it has a bunch of interesting tools, but the one we're interested in right here is Google Earth. We click that. It says, is it okay to open this file? I say yes. Takes us over to Google Earth, and it flies us right to Bear Lake. Splash. Let's back up here. Okay, looks like a nice lake. This is the border. North of that is Idaho, south of that is Utah. Now, like I said, we're going to assume that when the person said Bear Lake, they are referring to the portion that's in Idaho and not the portion that's in Utah. So what we do is, according to the point reference method, we drop a pin right in the middle of that locality name. In this case, that's the lake, right? So I'll go up here to the little pin tool, and I've got a pin, and I can move this around, and I'm going to put it right there, and I'm going to call this Bear Lake. And you'll see I have these coordinates. So I'm going to copy these coordinates. This is the latitude. Go over to our georeferencing calculator. That was here. And we already did the coordinates one. So we now select geographic feature. So again, we're getting this from, oh, in this case, the coordinate source. Where am I getting the coordinates from? Well, they weren't on the specimen. We're taking them from Google Earth or Maps that was created after 2008. So I select that. The coordinate format, they're in decimal degrees. And I'm going to paste this in here. So that first value for latitude was here. Go back here and get the longitude, -111 something, paste that in. The datum, like I said, this is the model of the Earth. Well, I happen to know that Google Earth uses WGS84, which is probably the most commonly used datum, at least nowadays. But if we were using a different map, say from a different country, or each state, and the US has its own particular map that many state employees are supposed to use, we might select that here. But in any case, we're going to take WGS84 because that's the datum used by Google Earth. And then our precision, basically it's how many digits we're going back to, or we're going out to. So you got 1, 2, 3, 4, 5, 6 digits. And we can only select down to, what is that, 5 digits I see here, but that's honestly very, very precise. It's about to the nearest meter or so. Okay, so this is this part of the georeferencing calculator. Now we have to fill in this part. So the radial of the feature is literally the radius of our lake. Now our lake obviously isn't a circle. I'll show you how to calculate that. So I'm going to leave the pin here so I know where I am saying the center of Bear Lake is. And I go up here to the measuring tool. You see this little ruler. And I've got the line tab selected. And I'm going to do this in, let's see, meters. So clicking as closely as I can to the center of, or basically where I put the pin. I did that. And now I'm looking for the extent or the part of Bear Lake that is furthest from my center. Now, ideally, you know, all the parts would be equally distant, but obviously it's not a circle. So we're going to pick, let's see, this is 8,700 meters, 7,200. I think over here, this corner, that's the furthest away. So I'm going to click it right there. And we've got 8864 meters. And I'm going to put that into the georeferencing calculator, 8864 meters. And I'm going to change that unit to meters. So this measurement, so this is the radius of Bear Lake in a sense, where we're saying the circle is that big at least. This measurement error has to do with the fact that, as you might have noticed, where I put the center of Bear Lake and where you put the center of it, at least the part that's in Idaho, might be a different location. Likewise, even if I did it several times, every time I clicked, I'm sure I get a slightly different location. And it was, if I tried to recreate the length of this line by clicking here and here again, I'd probably get a different distance. So there's that kind of an error that I am inadvertently introducing to this system. Now there's a way to calculate that. You can do this over and over and see how good you are. Of course, you can get more and more accurate if you were to zoom in and try to get the exact, say border of the lake. And you can say I overshot it by a little bit there. But what I do, honestly, to make it go a lot faster is I look at this value and I just take 1/10 of that and assume my error is that or less. So 886.4, and there we go. So we can click calculate. There we go. That's the latitude, longitude. That's the center of this portion of the lake, and this is uncertainty in it. Let's see what this looks like. So 9,760 meters. Zoom out. I'm going to go here to my circle tool. And yeah, I think I'm going to start. So I'm going to click in the center. 9,007 there. Kind of eyeballing it, but that's there. Okay, about 9,700 meters. So basically what we're doing is we're asserting that the specimen was collected somewhere within the circle. Now, assuming this is not an aquatic plant, most likely was not collected in the lake, but nonetheless, we still include the lake in the circle. Likewise, you'll notice that the circle includes part of Utah, even though the specimen was supposedly collected in Idaho. And that might seem a little bit inappropriate, but honestly, it's fair. Because if you're on the ground, it can be hard sometimes to know what state you're in or what county you're in if you're right in the line. As an example, many years ago, I was helping to collect some ground squirrels and I was asked to figure out what county we were. So I was looking at the topo map, and after a while, I realized that basically the county line was on one side of the picnic table. And now I might have been in error, but you can see it's very difficult to say exactly what county you might be in if you're right on the border. So it's possible that the specimen was actually collected in Utah and then inadvertently attributed to Idaho. So we can click, going back to the georeferencing calculator, click copy. We've got our values, paste those in, and there we go. Now, we might want to add some further comments about assumptions we made if those are so warranted. And here, I think it's pretty straightforward, but it's important if you make some assumptions that you cannot assume that somebody else would have assumed if they were also georeferencing, then to go ahead and note those particular assumptions. So that's our second type of locality description. The third type is a location with an offset. And I looked and looked and I could not find any specimens that were examples of this, but believe me, they do exist. So let's go with the present one, but add a 10-mile offset. So we're saying it's collected 10 miles from Bear Lake, Idaho, not necessarily saying north, south, east, or west, but let's go ahead and do that. Actually, let's go by the georeferencing calculator. And so we're going to select, let's see, distance only. So we're going to keep this all the same. So the center and so forth is not changing. And now we've picked 10 miles. Now, it's important here to keep it in the units of the description. And in this case, the description says 10 miles, not kilometers. We could, for example, translate this to kilometers, but I'll show you why that's important not to do in a few seconds. But in other words, we want to keep this in the native units. That means, though, we have to change the radial of the feature and the measurement error to miles or units of miles. So we can do that different ways, but I'll show you the little fast way to do it down here. So this is in meters, or originally was. We can paste it into this little tool, and we're going to change it to miles. So this is how many miles that many meters is. And remember, for this one, we just took 1/10 of it, so 0. Take out that decimal, and I'm going to change this to miles. So this is why at this point, when we're looking at the precision, this is why it's important to use the original unit of measurement. So our precision here is 1 mile, because we're going to assume that if I had been closer to 11 miles, I would have said 11. If I had been closer to 9 miles, I would have said 10. So our precision is 1 mile. And if I had translated this, for example, into meters or something, then this, selecting the appropriate one would have just not been possible. So this is an important aspect, and it's difficult to think about, but for example, say I had said 10.5 miles distant from Bear Lake. In that case, you were only sure that I had collected this specimen within plus or minus 0.25 miles of 10.5 miles. In other words, I would select half a mile as my unit of precision. Now, maybe I really did mean 10.5000 miles, but in this locality description, it's difficult and impossible to infer that with any kind of confidence. So we select the more generous precision. If I had said 10.4 miles, then we are fairly sure that if I had been closer to 10.5, I would have said 10.5. If I were closer to 10.3, I would have said 10.3. So in that case, we would have selected 1/10 of a mile as my unit of precision. So you can see how the units here should be interpreted. And there's a more specific set of rules that I would guide you to, and they're described in the Geo-Referencing Best Practices document. And it can get a little bit tricky when you get into those decimals and things like that. And also units of 10. So 10 is a small enough number that we can assume that, I wasn't eyeballing it and maybe I was 20 miles away or something like that. But once you get into 20, 30, 40, those nice round tens of numbers, then we assume that I was, unless I state otherwise, I was kind of eyeballing it. So if I had said, for example, an offset distance of 50 miles, we assume that it's anywhere between 50 plus or minus 5 miles. And likewise, if I'd say it's 200 miles away, then we assume it's anywhere within plus or minus 50 miles. Again, I was kind of guesstimating. But so let's go back to the example at hand. We've got 10 miles offset plus our radius, now expressed in miles. Our precision is 1 mile. We can calculate, and we've got everything here, and we can copy and paste it into our record. Okay, now we're all done. Good job. So before we go on to the next type of record, I do want to mention that these can be hard to interpret, and especially when they're very, very qualitative. So here's the kicker. For example, we may have a description near Guadalajara, state of Jalisco in Mexico. So let's look at Guadalajara. Notice there's the Guadalajara, Spain, Guadalajara, Jalisco. It might seem commonsensical that you'd be referring to one and not the other. And yet it's important to keep that in mind. So for example, once I was looking at butterflies that are native to North America, and I found one though, geo-referenced to Stuttgart, Germany. And I thought, well, that's odd. So I looked at that specific record, and indeed it was collected in Stuttgart, but it's collected in Stuttgart, North Dakota. I believe it was one of the Dakotas at least. But when the person saw Stuttgart, they said, oh, I know where that is. And they put it in Stuttgart, Germany. So it's always important to double check the fact that you might have duplicate place names, at least at a small level, but when you look at the country or state or something like that, it could be a very different place. So let's go to Guadalajara. Guadalajara is a very large city. There it is. And our locality description said near Guadalajara. Well, zooming out, there's a lot of near and as well as a lot of far from Guadalajara. So there's a very specific set of rules for how to interpret near or these kind of qualitative statements. And it's difficult for Guadalajara. If you had, for example, a mountain range, then you could use, say, for example, a topo map to help you delineate where the mountain range, or if it's a particular mountain, where that begins and where it ends, like basically kind of where the valley starts and where it stops. In some cases, though, I'll show you if I can zoom in well enough. This isn't always dependable. Depends on what the internet wants to do that day. well, shoot. Yeah, it's just not showing. Anyway, what I'm looking for are some of these. You can see this red pin here. Sometimes these show up for, I guess they would be suburbs of Guadalajara, but I'm going to make one up. Oh, okay, here's one. Let's take these two. So Santa Ana is, I guess, a suburb over here, and Santa Maria, I guess, is another suburb over here. So if you were to read a description that said collected in Santa Maria, now if you were on the ground in Guadalajara, or at least the greater region, you probably have an inkling for where Santa Maria ends and Santa Ana and begins. And I'm presuming these abut one another, but maybe there's something in between, I'm not sure. But just given this verbal description, collected in Santa Maria near Guadalajara, what we'd infer about the extent of Santa Maria is that it goes from basically the center, so to speak, of Santa Maria to, I've got my circle tool, turn that off. Come on, work with me, clear the line. Okay, it goes from Santa Maria to halfway between Santa Maria and wherever the pin would be for Santa Ana. So something like that. And I would use that as my radius. Now, that's one side of Santa Maria. You might also think about its distance to Guadalajara. And again, if you're on the ground, you'd probably have a much better sense for where one ends and one begins. But here, the base assumption is that it's halfway between Santa Maria and Guadalajara. This isn't the best example of how to do this because normally I do a lot more research and figure out, if I could, the actual boundary of Santa Maria, but at least shows you the general lay of the land in terms of how you would do it. Okay, the next type of locality description is distance at a heading. So in this case, there's a lot of description, but I've transliterated it here. It says at the edge of a lake, 15 kilometers north of Montalvania, state of Minas Gerais, Brazil. So we'll go to our Wikipedia friend. Montalvania, Brazil. And how did I spell it? Montalvania. Oh, and then of course, yeah, I went Wikipedia. Thankfully, it pulled it up. Here we go. We go to the coordinates tab, Google Earth. Yes, open that KML file, fly over here. And there it is. There's Montalvania, or at least that's where Google is saying it is. You notice the pin is trapped in a place where if you were on the ground, you probably wouldn't necessarily perceive this pin as being in the center of Montalvania. So let's zoom back out here. Pretty sure this is Montalvania. I don't know, not having ever been there, whether somebody on the ground would consider, say, this stretch here also to be part of Montalvania. But let's be as generous as we can using that philosophy we've already described. What we do in this case is, even though this pin might be in a sense at the geographic center of the named location, the rule says we should move it over to the nearest part of the location. So I'm going to put it right there for this example. I'm going to copy the latitude and longitude, and we are doing, here it is. So we're doing distance along distance at a heading. So 15 kilometers north. And we're using Google Maps, decimal degrees. I'm going to put the latitude here. Whoops, and the longitude, paste that in. We've got our datum, we've got our precision. Now, I want to point out something it won't quite make sense until we look at the next kind of description of a locality. These coordinates refer to, in this case, where we are starting from. So we're starting at Montalvania, and that's the coordinates for Montalvania, the center of it, and then going north. The next type of locality description, we're going to put the coordinates of where we end up. So it's important to keep that distinction in your mind. So the locality description said 15 kilometers north, so we can select all different kinds of directions here. We're going to collect just north. Our offset distance is 15 kilometers. Remember, we want this in the native units described or that were used in the description, so 15 kilometers. The radius of the feature, that's the radius of Montalvania. We're going to have to measure that. And again, we pick the largest distance. And I'm going to say, just to cut time short, that it's equal to this distance. So 2,740 meters. 2,740. What's my measurement error? In this case, I've got two different, remember my shortcut is to use the 10th of the larger distance. In this case though, this distance came from the locality description. If I put that in there, then I would use the 15. However, the 15 here is really in a sense inherent in the uncertainty generated by the person who made the specimen label, not mine. So this is intended to reflect my error. So in this case, I'm going to take a 10th of the radial of the feature. So 2,740 meters, or sorry, remember this should be in kilometers, right? So radius of, actually this is, yeah, 2.7 and then 0. Okay. So this is a 10th of the radius of the feature, and kilometers precision, it's talking about the precision of this to the nearest kilometer. Calculate, copy, put it over here. Okay, there we go. All right, so you can see it's fairly straightforward. There are these kind of, in a sense, hidden rules that you have to keep in mind, but as you go along, it'll become clearer and clearer. The next type of locality description, we're not going to walk through an example because it's very similar to the previous one. So in the previous one, we just had one direction. So it's 15 kilometers north. In this next type of locality description, it's basically using two different offsets. So we might say 10 kilometers north and 3 kilometers west or something like that. And so it's basically kind of going up and left or up and right or however it is. And in this case, what I would use for my error, again, depends on the fact that I'm measuring the radius of the feature. I wouldn't use these values as my measurement error. And then, of course, we do everything else the same. Okay. So the last kind of formal way of describing a locality would be a distance along a set path. And here by path, we mean literally a path, like a footpath, or it could be in a road, it could be a river, any kind of linear feature. And this is the example we'll be looking at. So this is Tomke Road, 2.1 kilometers north of the junction with Canyon Road in Mendocino County in California. So let's look up Tomke Road in Google Earth. Remove that. Tomke Road, a bunch of different Tomkes here. I've already done my homework. I know that it's Redwood Valley, but normally you wouldn't necessarily assume that. You'd have to do a little bit more homework. So there is Tomke Road, and it's this one right here. Now, we're looking for the junction with Canyon Road, and we could spend a lot of time going up through here trying to find Canyon Road. But in this case, it's going to take a lot of time. So we could type in Tomke Road and Canyon Road. Oh, and you know what? I've already typed this in, and so it knew exactly where to go. But if I had done this fresh, like without a history, basically in the program, it would have given me an error, and it would have said location not found. So what I would have done, and I wanted to show you this, is show you how to do it on maps, Google Maps. And this is a good example of where maps can be better than Google Earth. So I'd write Tomke Road and Canyon Road, all right? And again, it has the history memorized. So here it is. Now, this is nice. So you can see this is Canyon Road right here. It says Tomke Road. I can zoom out. It's hard to see where that might be. So what I would do normally is I would find a landmark, in this case, the Little Darby Environmental Center. Temporary close, that's so sad. And so I would hope that this would be in Google Earth. Type that in there. And sure enough, it's over here. Okay, it's right there. So I would use this as my landmark and then say, okay, I just need to go down here to the intersection. So anyway, and the computer outsmarted me. So let's go back to our locality description, because the locality description was relative to the junction of these two roads. So 2.1 kilometers north of that junction. And in this case, it's distance along a path. So we're literally going along the path of the road. We're not going 2.1 kilometers directly north of there. So we got our measurement tool. We're going to select the path tool, and we're going to put this in kilometers. So we're going to start where the intersection is, click it, and click the next part of the path. Click there, click there, click there, and I'm going to keep going. You can see the path length is accumulating here in the little box. Now, it's important to keep in mind that, let me do this in an improper way. I could do that, and yeah, I accumulated some path length, but you see my path is now off the road. So the more precisely you can zoom in and click where the actual road would be, as a car might be measuring the distance, the better you'll get. If you make a mistake like this, you can actually just kind of grab one of those little points and then drag it back and then keep going. Now, to make this fast, I'm going to do it in a bad way. So I wouldn't normally do this, but to speed things along, we're trying to get 2.1 kilometers, 1.8, almost there. Whoa. Okay, I'm going to put it right there. 2.24, that's a little bit too far. And there, that's 2.1 kilometers. Now, obviously, like I said, I'm really literally cutting corners. I wouldn't normally do it this way. So here's where we're ending up. And I'm going to save this. I'm going to call it whatever. So now what I do is I take the coordinates of where I ended up, and that's here. And that's what I put into the georeferencing calculator. So I'm doing distance along a path. And here's where I put the coordinates for the place that I ended up, which is, like I mentioned earlier, in contrast to the previous ways a georeferencing calculator, georeferencing something, which is in which case you put the coordinates of where you started from. So it's important to keep those in mind. So I've got these in here, nothing else has changed. The radius of the feature in this case is the radius of the place you started from. It makes a little bit less sense to start from, to think about the radius of an intersection. Of course, a radius, an intersection is a place, it's not a point. So yes, it does have a radius in a sense. But if our example had said something like 2.1 kilometers north of McPherson, well, when I say that, McPherson is this small city in Kansas, was I meaning the outskirts of McPherson or the center of McPherson, whatever it is. In that case, it would make more sense to include the radius of the feature. So in this case, I'm going to just assume the radius of the intersection is 0. There's an error inherent in that, but that's what I'm going to use. Actually, yeah, let's do that. Now, here's this measurement error. And again, different kinds of rules for different sorts of situations. Remember, my quick rule of thumb to make this expedited is to use a 1/10 of the distance of the values that are in the boxes above here, but I've already asserted this is 0. So if I use 0 here, I'd be asserting a no measurement error. But in this case, I had to go kind of point by point, section by section, 2.1 kilometers north of a particular location. So every time I clicked on the road, there's an error inherent in that because you might click in a different way. So in this case, I would use a 1/10 of 2.1, 0.21 kilometers. And my precision refers to the 2.1 kilometers. So it's to the nearest 1/10 of a kilometer. And now we're done. We click calculate, copy, and let's go. I'll paste it in here. I don't have it entered, but anyway, that's where it would be. Let's go back here and look at this uncertainty. So 269 meters in uncertainty. Google Earth. Let's zoom out. And we're going to pick our circle tool. It's the nearest meter, 269 meters, and zoom out. Okay, that's good. So we're asserting that the collection was made somewhere within this circle. But if we go back to the locality description, which is here, you'll notice up here it says locally abundant on steep west-facing road bank in sandy to gravelly soil. Now, we can't be very confident our ability usually to identify sandy or gravelly soil using Google Maps or Google Earth, but we can locate the west-facing side of the road bank, which in our example would be over here. So it might be possible, if it were profitable, to restrict our area to just this west side of the road bank, assuming the specimen was not collected over here. Now, in reality, you would probably do that in a very similar manner. Say, put the center here and then draw a circle that encompasses just the west part plus inadvertently part of the east part, if you wanted to be more precise. But anyway, we could probably stop here and not improve our situation too much further unless we wanted to be very, very precise as to where this particular specimen was collected. Okay, so that's distance along a path. The last type of a locality description I want to introduce you to is this one. And this isn't one that's explicitly in the georeferencing calculator, but I'm going to show you how to handle it in the georeferencing calculator. So this is from the Public Land Survey System, or PLSS. And the PLSS has locality descriptions that look something like this. So it's T28N, R9W, SEC28, and sometimes there's more. The way to interpret this particular one would be Township 28 North, Range, that's the R, 9 West, Section 28, and so forth. So the PLSS was developed and applied state by state, different times, depending on when the state got surveyed. And so there's different kind of method for each state, but here's in general how it works. So each state is divided into townships. You can see the squares here. Each square here is a township, and a township is 6 by 6 miles in general, sometimes a little bit not, but usually 6 by 6 miles. Quite often, there's at least one meridian in a state. Sometimes the meridian is coincident with a border, but in this case for Missouri, it's not. And so each township is numbered according to where it is relative to the meridian. So you might have township number 28 west in this example, indicating that it's west of the meridian, or township 28 east of the meridian, something like that. It's in practice, though, I'll show you, it's not so important to know the meridian of the state, because the tools that I'll show you kind of account for the fact that you may not always know the meridian that's being used. So each township then is divided into sections, and each section is 1 by 1 mile in length. And each section is also numbered. In this particular case, you can see it's 1, 2, 3, 4, 5, 6, going down and then across and so forth. So you might say that I'm in township, let's see, this in this example, it's township 9 south. So we're saying it's township number 9 south of the meridian for this state. And this is a generic state, it's not any particular state. Township 9 south, and maybe I'm in section 7, so I'm over here. Now I can be even more specific, because that only locates me to a 1 by 1 mile area. Townships then are divided, or sorry, sections are divided into quarters, and they're labeled northwest, northeast, and so forth. So I might say township 9, section 7, northeast quarter, and then I can get into quarter of a quarter. So I might be in the southwest quarter of a quarter of a quarter, and you can get into quarter of a quarter, and sometimes it can get a little absurd, but it'll get you into a finer located area. Sometimes you're not entirely sure what quarter you might be in, so you might say I'm in the north half of a section, or the south half, or the east half, or something, in which case you're only able to locate, you're only asserting that you're in one of these 2 squares, but you're not sure which square you're in. So this is how the public land survey system worked, and it's different for each state. Luckily enough, there's this really cool website called Earthpoint.us, had a lot of different tools on it, but I want to point you specifically to this particular tool. So this is a way to locate something using Google Earth uh, um, uh, based on a public land survey description of its locality. So we're going to go down here to this link here, and let's do it live. Here it is. So township range, search by description. Let's go back to our locality specimen. So this is in California. So you go back to the website, pick California. These boxes will update to restrict to the townships and whatnot that are only known from California. Let's see, township 28 North. So we select, so here's where you have to select meridian, but in this case, you're going to see it actually doesn't matter. And usually in my experience, it doesn't. So 28 North. Now it's populating these other boxes. While it's doing that, let's switch over. Range 9 West. Okay, range 9, we've got their easts, 9 West, and section 28. This tool doesn't allow you to go down to quarter sections or quarter of quarter sections and so forth, but I'll show you how you do that anyway. So now we just click Fly to in Google Earth. Do we want to open the KML file? Yes, we do. And it will fly us over here. And that's what we've got. So what are these various boxes? Well, let's find out. Let's assume that we didn't know. So I'm going to measure this just to see how long it is. The sides here. And that is pretty close to 6 miles. So that means this orange square is our township. Remember, I said those are 6 by 6 miles. And then by inference, I'm not going to measure it. You can see this is 1 by 1 mile. I'm going to zoom in here. I'm going to clear that out. So this is our, let's see, so this is our township. This is our section. And there we go. This is our section. And now let's go to, let's see, range 9 West. So each of these, it's hard to tell exactly where these are, but you can click on the various little dots and then through the metadata inherent in each one, figure out which one is the particular range, or sorry, which one is the particular section that you're looking at. And then sometimes you have to kind of eyeball it to say, okay, it's in a quarter section that's going to be up here. But you can take then, the same tools that we've been using before, say it's, there, and then draw a radius encompassing the box and so forth, and then plug that into the georeferencing calculator. So in a nutshell, this is a quick tour of how to apply the point radius method of georeferencing. And like I said, this is a quick tour. What I've shown you is insufficient for doing this in a robust, repeatable sort of manner if you're georeferencing a lot of specimens and you want to do it in a scientific manner. It honestly just takes a day long, at least, kind of workshop to do that. But if you go to those links at the bottom of the georeferencing calculator, it'll describe for you how to apply this yourself. So this is a good entry point, I hope, to do that. Couple notes though before we end, some tips, trips, and some flowers for you. Botanical specimens, at least, are often not georeferenced where the actual plant is, and this is information I have from real curators on the ground. Usually they'll drop a pin basically in the rough center of where they're collecting and then collect in the surrounding kilometer. So even if you have GPS level coordinates of a locality, it doesn't necessarily mean that the precision with which that location is associated is equal to a GPS accuracy. And GPS accuracy is somewhere within 3 to 5 meters, usually if you have good satellite coverage. So you're not in a very forested area or not in a canyon or something like that. And the same thing goes for a cell phone. So it's important to take with a grain of salt GPS coordinates, especially for botanical collections. Excuse me. Oh yes, this actual tip is a little bit different. So if you're georeferencing a lot of specimens and you have them in a spreadsheet, quite often collections are close to one another. And after you spend some time locating a place, especially if it's difficult to locate, it can be really expeditious to see if there are other places or other collections that are collected close to that original location. So in our one example, we're looking at Tomkey Road. What I would do in the spreadsheet is I would search for Tomkey, because that's kind of an unusual name, and I would see if there are other collections close to Tomkey Road, and then just kind of go from there. So it can really speed up the process versus trying to find every single place again and again de novo. Like I just said, a lot of herbarium specimen collections, at least, are not necessarily done at the point of a GPS pin. If you're using specimens that have been previously georeferenced, then keep in mind that some of them may be geolocated to the center of the smallest possible geopolitical unit. In other words, if I were cleaning the records from this specimen or from this species, and I did at one point, I would be a little bit suspicious, say, of this point, and this point, and others as well, because to my eye, at least, they look like they're in the center of those particular states or provinces. Now, they may have been collected there and may be valid records, but I would at least inspect them to see if they are as accurate as they, in a sense, might seem by just looking at a point, a set of points here. Now, this said, there are probably a lot of records here that are also geolocated to the center of counties. And at this scale, that is really hard to tell apart from ones that may not be. That may not be. For example, this record is not at the center of Montana, but it might be at the center of whatever county is there in Montana. Likewise, it's going to be really difficult to tell specimens geolocated at centers from of counties or whatever, or even of the state from other records here. Anyway, it's just something to keep in mind if you're using other people's georeference specimens, where the specimens have been collected in a manner of as so described. The other thing I would beseech people to do is please do not georeference specimens that really shouldn't be georeferenced. Per example, this is two specimens up here. These were georeferenced to the stores in which they were bought. Now, maybe I'm not being extremely imaginative, but I can't think of any kind of use for knowing why, knowing the location of a store, unless I wanted to go back to that store, but even then the address would have sufficed to purchase this kind of specimen. It doesn't indicate any sign of any kind of natural conditions under which the species was collected. The most ridiculous example I've ever found of this is this specimen here. And you can see in relation to where the other occurrences fall, this isn't a wild outlier. Yes, it's the only one in California, but this is probably the only one here in South Dakota here. So it's not that there's only one per state. There are other outliers, so to speak, and they kind of fall within the realm of possibility that maybe there is a specimen here. So anyway, I did decide to look at this because I thought it just looked a little bit strange. And I found that the locality description said it was collected from a bouquet as part of a wedding. And I thought, that is absolutely ridiculous. Who did this? So I looked at the collector and I knew the person, and I realized, oh yes, he's a very eccentric person. I can see him doing this. And I thought, wait a second. I looked at the date, and up to then I only looked at longitude, latitude. I looked at the locality description, that is the municipality. And sure enough, I had actually been at that wedding, and not only that, I had officiated it, and here is proof. There's me officiating the wedding. I don't think this is the offending bouquet, but in a sense, I'm offended that this record was geolocated to that wedding, because that conveys to me, at least, I mean, it's personal, I guess, but otherwise it conveys no useful information about the conditions under which that specimen would actually be growing out in the wild. And I'm not showing you quite a few other specimens which I removed from here because they are geolocated to the greenhouse or to an experimental section which may have been receiving water or drought treatments or whatever, you don't know, from the specimen database. So a lot of other specimens have georeferenced to places that they shouldn't be georeferenced. And if you're doing this for yourself, you may georeference to one of these locations, But then 5 years later, somebody says, hey, do you have records for such and such a species? You say, yes, you pass it on to them, forgetting to tell them that you georeference something to the greenhouse or whatever is growing in. And this is not an uncommon problem. I've found polar bears georeferenced to the Omaha Zoo. A colleague of mine found a giraffe georeferenced to San Diego Zoo, and so on and so forth. So anyway, end all, the end point here is that please don't georeference specimens that shouldn't be georeferenced. So in summary, regardless of whether you use the point radius method, I would encourage you to use a very systematic sort of method for georeferencing, one that gives you not only a set of rules for assigning coordinates, but also uncertainty inherent in that coordinate description, because that is very important for allowing other people then to be able to match that record, say, for example, with confidence to climate conditions or soil conditions or whatever it is associated with the fact that the species was actually located there. Also encourage you to check out georeferencing.org, far many more tools there that would be of use. And then finally, I also want to point you to a webinar that we recorded at the beginning of the COVID lockdown on using museum and herbarium data in ecology, evolution, and conservation. That's at our website. I'll show you where that is exactly. If you go to our website, you'll see this drop-down menu. Here's the webinar. Talks about not just georeferencing, but many other issues that you might have when you're using this kind of specimen data. And then we've also got a workshop on using species distribution modeling. And then, although it's not shown here, I'll also include the link for this particular workshop, which we're recording right now. So I'm Adam Smith. I'm enjoyed talking with you, and I hope you've learned something useful. Thanks a lot.